let's look at the effect of temperature on a chemical reaction from a kinetics standpoint. So, for the following chemical reaction, the forward rate constant is larger than the reverse rate constant, this chemical reaction here. What does that mean about the equilibrium constant for an increase in temperature? Is it going to increase, stay the same, or decrease? Think about that for a minute and make a selection. Let's look at a possible explanation for each answer. A larger Kf means the forward activation energy is larger. Thus, the products are favored and K should increase. B, both Kf and Kr adjust the same with temperature, so K doesn't change. Or C, a larger Kf means the forward activation energy is smaller and Kr changes faster with T. This favors the reactants and K decreases. Think about those three and make a selection. We're looking at the effect of temperature on an equilibrium constant from a kinetic standpoint. So the equilibrium constant is the ratio of K forward to K reverse, the rate constants. So we should be able to predict the temperature effect on that equilibrium constant. So we're told that K forward is bigger than K reverse. So the forward reaction is fast relative to the reverse reaction at equal concentrations, of course. This doesn't give us the whole rate. The rate depends on the rate constant times the concentrations. So these two rates can equalize if the concentration of products builds up. But what this ratio tells us is that the rate constant for the forward is larger. That means the activation energy for the forward is smaller. There's a lower barrier. That's what makes the forward reaction intrinsically faster. The reverse activation energy, slightly larger. Now, if the reverse activation energy is greater than the forward activation energy, how does that affect how the rate constants vary with temperature? Well, the rate constants vary with temperature by this expression here. It's exponential in the temperature, but it depends on the activation energy. The larger the activation energy, the more sensitive the rate constant is to a change in temperature. So for a large activation energy, K changes a lot with a small change in temperature, but for a smaller activation energy, the change isn't as large. So what we find is the reverse reaction is more sensitive to temperature because of its larger activation energy. That means the ratio of these two, which forms the equilibrium constant, the reverse rate is more sensitive with temperature. This one will change more dramatically. This will get larger with temperature faster. That will make the overall equilibrium constant get smaller with an increase in temperature. So for this, the equilibrium constant decreases with temperature. Now there's another way you could have looked at that. You could have said, well, this K forward greater than K reverse means this orientation of the activation energies, which means this is an exothermic chemical reaction. And if it's exothermic, heat is a product. I increase the temperature, that favors the reactants and leads to a decrease in the equilibrium constant. Two arguments that lead to the same conclusion for the equilibrium constant and temperature.